get started. So everyone on Zoom, can you hear me? I don't forget to unmute myself, right? Okay, perfect. Okay, so let's get started. Yeah, so in this lecture, we are going to continue to talk about, essentially different query languages to query your data or knowledge stored in relational models. So just like before we talk about kind of different query languages, let's try to recap a little bit about what we have been learning in the last lecture to make sure we are on the same page about what is relational model. So essentially, in relational model, our way of thinking about our data, thinking about our knowledge, is they pretty much fit into something look like a table. Okay? It has a name, it has different columns or attributes of the information of the same type, right? And you have different rows corresponding to different instances of relationship between all those values. And more formally, if you want to define your data in a relational model, there are two components. There is the schema, which essentially tells the system what your data looks like. Okay? So schema is a database schema, is a set of relation schema, and each relation schema contains the following: has the name of the relation, have a set of attributes, and have a primary key. Okay? And for each attribute, you also have a name, and you also have a domain, which is the data type that you can fit into that attribute. For example, if you want to store student information, right, you could write down a schema look like this. This is a student's relation with a student ID as a primary key, and then you have 4 other attributes. What this really tells the system is, okay, my data actually look like something like this. It looks like a table. Again, for schema, it's just what the data looks like. It has nothing to do with the content of this table. You can think about schema as something like essentially the header of this table. And then we have the data that you can actually store within a relation, and that is what we call an instance. So for each relation, right, assuming we have relation R with n different attributes, an instance is pretty much a set of tuples that satisfy all those domain type constraints. So this is essentially formally what it is. Intuitively, if you think about the schema as the header of your table, you can think about the instance as the content of the table, which is a collection of tuples. Again, if you have the student relation look like this is one valid instance of this relation. Right? As you can see, now we have 3 students. Each one of them has different information. And then we talk of different ways to query your data. Right? Assume your data is organized in a relational way. What is a query? Right? A query is a function that takes as input one instance of your database and output another relation. Okay? This is a signature of a query. And there are multiple ways you can actually express your query. And in the last lecture, we talked about one specific way is by query the data using a relational algebra expression. In this lecture, we are going to start from there and talk about a whole collection of different query languages. We have our relational algebra, which we will talk a little bit deeper today, but we will also talk about some other query languages, for example, relational calculus. We are going to talk about the relationships, right? The functions you can express in different type of query languages. Some of them are more powerful than the other, right? And we are going to establish some relationships between these different query languages. We are going to talk about some other query languages called domain-independent relational calculus, right? Understand their relationship between different query languages and some more restrictive set of queries that you can write. Hopefully we can finish this today, right? And then we are going to talk more on the practical side to have some practical query language that you can actually write to query a real database. So we talk about what you can write in SQL, right? So a smaller set of SQL queries with only select from and where. We talk about a larger subset and we talk about the full SQL kind of specification. So for each subset of SQL queries, the practical thing you can write, we actually also talk about the relationship with those more theoretical query languages. So this is what we are going to do this week and next week. We are going to go through different type of ways that you can query your data in a relational form. And we are going to try to understand the relationship. So last time we have something that we didn't finish for relational algebra, right? Let's try to look at that. If you want to describe relational algebra as a query language, the intuition is actually pretty simple, right? My relation are sets. They are set of tuples. So there's nothing stop me from querying them using set operations, which is pretty natural, right? There's a whole bunch of set, and you want the information out of it. What can you do, right? You define a whole bunch of set operations, and you write expression using them, right? So it's a very natural idea. Just look at this one example, right? So this is the database we have been looking at from last week. Assuming you want to write a query that looks like this. That is, I want to have all the courses that students cannot take because they fail the direct prerequisite. Okay? Assuming this is the query that we want to write. What should we do, right? So before you write this query, let's think about what information do we need to answer this query. What information do we need? Yeah, we need the student information to make sure we have a list of students. We need the prerequisite relationship, right, to make sure we know which course is a prerequisite of which other courses. We need the test relationship to make sure we can filter out the student who passed the prerequisite, right? And if you have these three pieces of information in these three different relations, we can start to write down a relational algebra expression to answer this query. What should we do? I mean, there are different ways for to write this down, but I'm showing you one way, right? One specific way is, okay, let's join the student relation with the test relation, okay? And then I will filter, do a selection over the join such that I can filter out the pair that with the grade lower than 4.0, for example, and then you get a relation that looks like this, right? You do a natural join between student and the test, which essentially you try to match all those pair of tuples. You only keep those tuples that matches on the personnel number column. And then do a selection on the grade attribute. Once I have this, I can actually join this kind of relation, like this intermediate relation, with, for example, the requires relation. To say, yeah, so if this student failed this course, this is the next course that relies on this one that student cannot take, right? You join that with the requires relation, it gives you something that looks like this. And in the query, we want all the students, so you do one projection to only keep the student ID and also the lecture ID that give you something like this. So this relatively long relational algebra expression, right, is one way to implement this query. So far, so good, right? It's relatively straightforward. We define a whole bunch of set operations over relations, and then we just write expression. So one problem of relational algebra, not a problem, but one property of relational algebra is it's not really declarative. So let's see what this means, right? By saying it's not declarative, we mean that if you want to write one specific query, there could potentially be multiple ways to achieve that. So now let's take this very simple query. I want all the students who take database course. How can I write this down? To write this down, there are multiple ways to do that. You could say, okay, now let me do a natural join between students and attendance, okay? To have a student and all the courses they are taking. And then I join that, a natural join with lecture, and then I subselect on database and project on students. This gives you all the students who took database, right? This is one way to implement this query. But there are other ways for you to do that. An alternative way for you to do that could be like this. I could do a cross product, not a natural join, but a cross product between student and the lecturer, okay? I get all the pairs of students and lecturers. If there's a 1,000 students and 1,000 lecturers, I get 1 million of those pairs. And then natural join that 1 million pairs with the 10th relation, okay? And then I do my sub-selection on database as a title and project to student ID. It's not hard to see that these two relational algebra expressions give you the same thing, right? Under the current schema, they give you the same thing. But if you look at the execution of these two queries, you can realize that for the second query, the thing in the middle is super big, right? Because that's pretty much give you the cross product between all the students and all the lecturers without any filtering, right? If you ask the database to run the second query for you, it's going to be very slow, right? Because it have to do this. It doesn't have other information to optimize this query for you because you tell the database do this, right? So this is what we mean by something is not really declarative, because you are telling the system how to get the answer for you. The moment you tell the system how, right? The system really doesn't have a choice to optimize that for you because you tell me this is what I need to do, so I do it, right? That's the contract between you and me. Ideally, if you are a user of a database system, we really do not want this to happen. We do not want our user, before they write every single query, try to reason about whether this query is going to be fast or not. And that is why later you are going to see in real database systems, the user are not writing a relational algebra query because it's super hard for them to reason about which one is fast, which one is slow, because it highly depends on your data, right? So what we are going to try to do is try to give system some higher level abstraction to say, this is what I want, and you figure out how to get it done, right? So that is our goal. So in practice, in relational database, often you are not writing relational algebra, but it's very important for you to know that's one query language that we're going to see the relationship between relational algebra and that fancy high-level declarative language that we are going to see really soon. But now let's go a little bit deeper into relational algebra. So far we have a very powerful query language, right? It can write a whole bunch of fancy queries. Do we have limitations? Can you think about some function, some query, that we are not able to express in relational algebra? That's very important, right? We need to know what we can express. We also need to know what we cannot express. That's the two sides of a query language. So one limitation of relational algebra is by looking at this query, okay? I have a table, I have a relation, with two attributes. The parent relation, okay? The first attribute is the parent, the second attribute is the child, okay? And the query is, okay, I want to find all ancestor of B. B is a person. So what should I do, right? So one thing we could do is, okay, let's try to find out the parent of B, right? I think we should all know how to write that so far, right? You take the parent relation, you subselect child equals to B, you project on parent, right? This gives you the parent of B, right? But this is not all the ancestors because I want to go up in the family tree. So we go one level up, right? We take the parent of B and join that with the parent relation, and then we get essentially the grandparent of B, right? But we want to go up. Let's get a great-grandparent of B. But it's still not all the ancestors. Because to get all the ancestors, I need to keep climbing up the ladder of the family tree. That will actually never stop, right? Before I'm writing this query, I have no idea how many levels I need to go up, right? So in all the operators that we have been learning so far in relational algebra, there's no operator gave me something similar to a for loop. So that's actually a pretty fundamental limitation of relational algebra. I mean, it's limitation in the sense that it's a limitation of expressive power. Okay, this is something that it cannot express. Okay, so we'll talk about the solution to this maybe around Easter, right? So there's something you can do in database to actually write such a query. But in relational algebra, this is one limitation, right? There's no for loop. Okay, there's no recursive structure. That's another way to say that. So another thing about relational algebra that's interesting is we are learning this in the context of a database, but the impact of relational algebra actually go beyond a relational database system. So you can see that in many kind of modern data analytic frameworks, such as pandas or data frame, right? So we will not go into this example. We are going to have one TA session, right, for our TA to go through some of this example about how you can write relational algebra, right, in other type of languages. And also there are a whole bunch of extensions about relational algebra, right? So let's go through some of them. So far, when we talk about relational algebra, we are always assuming your relation is a set, right? So there's no duplicates, right? It's a set of examples. There's no order, there's no duplicates. In practice, what's often very useful is to treat relation as a bag of examples. It's a multi-set, okay? So essentially, one specific thing can kind of appear like multiple times. So there are kind of extension of relational algebra from the set semantic to a bag semantic. So we are not going to test it in the exam, but it's something that's very interesting for you to know, right? Because when you extend the whole thing from the set semantic to a bag semantic, there are a lot of interesting things that you kind of need to consider. So in this extension, right, each relation is a bag of tuples. You can have duplicate tuples in the same relation. For example, the difference for set, right, you have 1, 2, 3, there's 3 different elements. Right? For bag, you can have the one element appear multiple times, for example. That's the difference between set and bag. When really extending the relational algebra thing from set to bag, there's a whole bunch of things you need to be really careful because they look very similar, but they are actually pretty different. The first thing is the operator semantics could be different, could be very different, actually. For example, if you take the union of a bag, right, that's going to look something like this. There's no deduplication of tuples. We're going to do a union of a bag. We're going to do a difference, right? That's also kind of interesting, right? When you have, for example, on the left-hand side, right, like a 2-element 1, you take a difference. Yeah, I mean, you get another element 1, right? So this is the operator semantics are different. The laws for you to reason about those operators will also be different, right? So I think in set semantic, this is always hold, right? You have R intersection with S union T, right? So if you are doing a set semantic, right, the left-hand side is actually equal to the right-hand side. But when you have a bag semantic, right, so that's actually not always the case. So one like the counterexample is when you set R and S and T to be the same, they have a single element 1, right? And then you can do the exercise, and you can see if you have a bag semantic, the left-hand side is going to be actually different from the right-hand side. So when you do the extension, we will think about how to reason about those operations in relational algebra with the bag semantic, right? Often, a lot of the rules that you are kind of familiar with under set semantic, because that's pretty much we have been dealing with so far, right? So it's going to be very different when you are talking about the bag semantic. And also, there could be new operators. There could be deduplication kind of operators to eliminate all those duplicates, right? And there are other extensions of relational algebra. We are going to just talk about it a little bit. In practice, you can extend relational algebra with sorting, right? So introduce orders. You can also have group and aggregation, those type of things to extend relational algebra. So modern system of relational algebra contains all those extensions, right? But in this course, when we talk about relational algebra, we assume it's a set semantic, okay? And we assume it only contains those standard set operations that we have been talking about in the last lecture. But it's very good to know they are extensions. So this is all about relational algebra. This is one query language that we have to really query information stored in a relational form. Now let's talk about another query language, something that we call relational calculus. If you think about relational algebra, right, summarize that in one sentence, is my data is set, so I query it using set operation. If you look at this statement, right, so you might say, yeah, no, but relations are not sets. Relation is more than sets. Because relation is not a set of abstract mathematical objects. Look at all the information we put in a relation in the previous example. We put student information, we put professor information into that relation. It's not a set of abstract objects. It's way more than that. By only treating it as a set, you are actually constraining the power of what system can actually do for you. Relational calculus is actually trying to go beyond this view, try to go beyond the view of treating relations simply as a set of tuples. In the view of relational calculus, we are treating a relation as a collection of facts. That's the factual information you know about this universe. We are taking this view, right? How to get new facts given an existing collection of facts. If you take this view, you are not going to query it using set operations. What are we going to do? We are going to query it using logic. Because that is what we know of how to create new facts given an existing collection of facts. So now let's try to recap a little bit about, not recap, but try to refresh our memory about logic, because we are going to kind of use it to query my data. So I think most of you guys have know what first-order logic is in your first year, right? So now let's quickly go through it to make sure we are on the same page about all those kind of terminology, to make sure we can go deeper into relational calculus. So what are the things you can express in first-order logic, right? If you want to say, yeah, so I have two persons, Alice and Bob, they both know arithmetic, right? You write something like this. You have a knows predicate, right? Knows Alice arithmetic and knows Bob arithmetic. Everyone knows how to parse it, right? How many of you knows how to read these two logic formula? Raise your hand. Okay, so then we are going to go through this quickly, okay, to make sure we are on the same page. You can also express things like all students knows about arithmetic to say, yeah, for all x, if x is student, it implies x knows about arithmetic. You know this in your first year of study. So again, I'm sure you already know this. For a logical system, there are two different components of that. There's a syntax, there's a semantics. Okay? Now let's just refresh our memory about the syntax of first-order logic. So there are terms, right, referring to objects. Right? There are constants. For example, there's Alice, there's Bob. They are all constants in my logic system. There are variables, right? And then there are function of terms, right? For example, you have the function sum, 3x, that returns 3 plus x, something like that, right? Just functions. So these are the terms I have in first-order logic. And then we can define what is a formula really mean. A formula is, I say pretty much, you remember the recursive definition of formula, right? So there is the atomic formula called items. They are predicate applied to terms. For example, have one predicate called knows. It applied to two terms. One is variable x, another is constant arithmetic. But this is an atomic formula, right? This is one formula. You can connect different formulas, right? You can say students x implies knows x arithmetic, right? On the left-hand side and the right-hand side of this implication, you have two formulas. In this case, both are atomic formula, right? And you can connect them using logic connectives. And then you have quantifiers, right? You can say, yeah, for all x, which is a variable, student x implies knows x arithmetic. This is pretty much what you can write in first-order logic in terms of syntax, right? So again, we are not going to go deep into this, right? We are not going to be too formal about how this is defined. Just refresh your memory to make sure we are on the same page, that when we talk about first-order logic, what do we mean by that? So, and given this, you can write a whole bunch of statements or sentences, right? For example, say, yeah, there's a course that every student has taken. For example, take this natural language sentence. Yeah, you can write a logical formula to describe that sentence, right? You can say, yeah, essentially this essentially says there exists y, that y is a course, and in the meantime, for all student x, if x is a student, it implies x takes y, right? This is a precise logical expression of that natural language statement. But what does it even mean? You write down that expression. What does it even mean? And to answer that question, we need to go to the semantics. And that becomes pretty interesting, right? So assuming you have this logical formula, okay? There exists a course that all students take. Is this true? Right? This is a logical statement about this world. Is this true? Right? So it depends, right? It depends on the world that we live in, right? So we could live in a different type of worlds. We could live in a world that looks like this, that database is a course, machine learning is a course, Alice is a student, Bob is a student, Alice take database, Alice take machine learning, Bob take database. This could be one universe that we live in. Under this universe, I think it's very simple for you to check that this formula is true, right? Because you can find that course is database. You set y to database, the whole logical formula going to evaluate to true under this world. But you could live in an alternative universe that look like this, right? In this universe, Alice never take machine learning. If you live in this world, this formula is going to be false because, yeah, not all the students take all the course. I mean, there doesn't exist a course that all students take, right? So giving a logical formula, that's a syntax. That's the logical sentence you can write down. But what does that sentence mean? Whether it's true or whether it's false, as we can see, depends on the world that you live in. So we have to model that. So the way to think about this is for each of this world, it's actually give you a way to interpret each predicate. Just look at the thing on the left-hand side, right? So you say, yeah, the predicate course, here's how I interpret it. Database is a course, machine learning is a course. I concretely say, yeah, so for this predicate, right, these two constants going to evaluate to true in my world, right? And naturally we call this interpretation. I think you all remember this concept, right? Do you? Who remember interpretation? Okay, great. So let's go through some of this, right? So to define the world, right, you have a domain. That's all the objects, all the possible symbols you can have, right, in this universe. Here, for example, the domain could be database, machine learning, Alex, Bob, whatever constant I'm not using here, right? There's the domain. And then there's the interpretation of each predicate, which is a function that maps the name of each relation to a collection of tuples that is true under this predicate. For example, in this world, right, so we have the interpretation of the course, which is, okay, so that contains database, contains machine learning, and we have the student interpretation, which is Alex and Bob, and we have interpretation of takes, right, which contains a whole bunch of pairs, Alex database, Alex machine learning, Alex Bob, right? That's the interpretation. Put domain and interpretation together, you get something called model, right? And then this can actually precisely define the semantic or the formula is, if you write this, right? It means that this formula phi evaluated to true under this model, okay? If you write this, it means that this one evaluated to false under that model. Sorry, there's a typo here. Let me try to fix it. Yeah, evaluated to false under this model. So we are pretty much done about our recap of first-order logic. So now let's look at this formula, right? The only difference is I don't have a quantifier on y anymore, right? I'm just still valid formula. The y is a free variable, right? That's how you want to talk about it. It is true under model M, right? Again, it depends, right? Here it depends on the specific value you have on this y variable, right? If you have y equals to database, then this formula phi prime is true. If you have y as, for example, machine learning as a constant, the phi prime is false under this world. So the way that we have to model it is by having the notion of assignment, okay? What is assignment? Assignment is a function that maps all free variables to a constant, okay? For example, here are two example assignments that we could have. We could assign the value of y to database, or we could assign the value of y to machine learning. And under different assignment, this logical formula is going to have different truth value, right? For example, under assignment alpha, right, the phi is going to evaluate to true in this world. Under the assignment alpha prime, right, this formula is going to evaluate to false in this world. Let's try to fix it. Right? So that's pretty much what we need from first-order logic. Okay. So just to recap, this is logical formula. What do we have in first-order logic? We have the domain, contains all the symbols. We have interpretation, which is the collection of things that's true under this predicate. This gives us a model, and we have assignment, right? And then the formula can be true, can be false, given a model and assignment. And we can, given this, we can start to do interesting things. For example, okay, now we have the model, we have the assignment, and we have this formula, right? Find me all the variable assignment that make this formula true under this model. This is something you are able to write down precisely at this moment, right? How to write it down? Yeah, it's this set. I'm giving you all the assignment such that this formula is true under this model and this assignment, right? In this case, that's going to give you database because that's the only possible assignment on y that make phi to be true. This is pretty familiar to you guys, I hope. This is what you learn in the first year about first-order logic. Now, try to look at this, right? Because I can arrange things in a way that kind of familiar to a database person. Look at the interpretation. What is that? The interpretation, of course, are two constants. The interpretation of takes, right, are a collection of pairs. There's nothing stop you from arranging it such that it looks like something like this, right? I can put down those kind of not as a site. I can lay out them to look very similar to a collection of tables, right? There's nothing stop me from doing that. I'm the signature matrix. It's a collection of tuples. And then for the answer of this here, right? Yeah, let's find all the variable assignment that makes this formula true under this model. That pretty much looks something like this, right? I could have a whole bunch of possible assignments that make this formula true. I can arrange them as a table. And how to get from the interpretation to all the possible assignment, you have a formula. This is a logical formula I want to understand. I want to find all the possible assignment of this logical formula that is true, that makes this formula true under this model. And this is how we are going to make the connection between first-order logic and the relational calculus. The intuitive way to think about relational calculus is like this. Your first-order interpretation is your database instance that you want to query. And every single query you are writing is a logical formula. And the semantics of answering that query is to find all the possible assignment of the free variable that make this formula true under this interpretation. When you are using a relational database, when you are writing a single query, underneath the cover, this is what you are doing. You are not doing some relational algebra thing. You are actually trying to infer new fact using an existing collection of facts. So this is also how we connect these two things. And what we mean by if relation are facts, we can query it using logic. Now let's make this a little bit more concrete and try to define it in the context of relational calculus. So we have seen relational algebra queries, right, which is a whole bunch of set operations, right? If the system follows step by step, it can give you the answer. Unfortunately, that's not what we want for the user because we want something that's declarative. We want to specify what we want instead of how to get it. And that gives you something called relational calculus. If you open the book, what we are going to talk about is called domain relational calculus. There's another counterpart of it. We're not going to talk about it. So the high-level intuition is to map each relation in the relational model as a logic predicates, and relation instances as the collection of facts or the interpretation of that predicate. So for example, if there's a one tuple, right, 0, John Zurich, exists in that relation customer, it means that if you treat customer as a predicate, inside its interpretation, there's a tuple, 0, John, and Zurich. That's the connection. And once you take this view, you can write down your query as a logical formula. Okay? So you have the product relation, you have the customer relation, you have the purchase relation. Right? So how can I then you can actually write down a query that looks like this, right? This is all the product ID and the customer ID that participate in this join of these three different relations, right? If you treat each relation as a set, this is essentially what you are writing. On the left-hand side, that's a relational calculus query. On the right-hand side, that's the definition if you treat relation as a set. If you look at this query, right, what is the result of this query, right, the answer of this query? Essentially, all the PID and CID tuples belong to the above set is the answer of this query. It's kind of easy to see that this query gives the same result as this relational algebra formula, right? So if you go back, look at this relational algebra formula, and look at that kind of like logical formula, it's very easy to see that it will give you the same thing in the result as the answer to this query. But the difference is if you look at the logical formula and compare that with relational algebra expression. In the relational algebra expression, we cannot specify how to do the join. You need to join customer with purchase first, and then join that with product, right? I give you the join order. This is what I want. In the logical formula, I never have done that. In the logical formula, it's a conjunction of different predicates. I don't care how you join them together. You could join product with customer first and then join with purchase, or could join customer with purchase and then join with product. I don't care. They are logical conjunctions, right? That's what we mean by something being declarative. It's by writing your query as a logical formula, you actually do not specify how to get it done, right? That's the difference between relational calculus and relational algebra. We can go a little bit more formal to define domain relational calculus. So again, the schema of the database is contains the schema of a whole bunch of relations. Here, each Ri is a relation. And the relation schema for each Ri, right, contains a name, the R, and a whole bunch of attributes. Each attribute has a name, AI, and also has the domain of that attribute. We also need a domain, right, which contains infinite set of constants that you could put into your relation instance. You have the domain. It's very important to know the domain is actually infinite. We have infinite amount of constants. And a database instance, right, is pretty much look like this. You have your relation R, right? So an instance of this relation, right, is a subset of the cross product of the domain, right, which have the similarity as number of attributes, right? So IR, which is the instance of R, is a subset of domain to the n, right? N is number of attributes. And in database, we always assume this instance is finite, okay? It's a finite number of tuples in the domain. Why is finite? Right? Because I need to store them somewhere, right? I'm building a database. I cannot handle infinite amount of facts stored on my hard drive, right? It's finite. So instance of a database, what do we mean by database instance? Yeah, it's a function that maps each relation name to its instance, to an instance, okay? And an instance of relation is a finite set of facts over the relation, right? An instance of database is a finite set of facts over all the relations. What do we mean by query? So a relational calculus query looks like this. From the syntax, you give me a first-order logic formula phi with three variables, x1 to xk. This gives you a relational calculus query that look like Q phi, okay? Which is that site. Right? It's defined by the three variables in like in this formula, and also this logical formula. This is a query, okay? This is a relational calculus query. What is the semantics? What do we mean by the answer of this query? The way to think about it is each relation in database corresponding to a predicate in first-order logic. Each instance of this database or relation corresponding to the first-order interpretation, the world that you can assume that's true, all the collection of facts that assume is true in first-order logic. Assuming you have assignment, map variable to a constant, the answer of this query over this interpretation over this relational database instance is all the possible assignment of free variables in this formula, such that this formula is true under this interpretation of this database instance and this assignment. This is the semantic of a relational calculus query. So just look at this example, right? Assuming we have this kind of like a database with three different relations, assuming we have a relational calculus query, look like the thing like in the above, right? You try to, the free variable there is PID and CID, and then you have in your formula, right? So there exists N and P such that you have product PID NP conjunction with there exists variable S, right? What follows? If you look at this, right? So is the tuple 0 and 0 in the answer? Well, in this case, yes, right? Because I'm able to find that assignment, right? So here I have assignment that assign PID to 0 and CID to 0, right? I'm able to find the N and the P such that this formula is actually true, right? When that happens, the tuple 0 and 0 is actually in the result of this query. And then we can also reason about other tuples. For example, if 0, 2 in the answer is actually no, because if you assign PID to 0, CID to 2, that formula going to be false under this interpretation. Okay? That's the formal semantic of relational calculus. So, any questions so far about relational calculus? No? Okay, now let's then take a break. When we get back, we talk more about relational calculus. Yeah.
Hallo zusammen. Wäre nett, wenn ich kurz eure Aufmerksamkeit haben dürfte. Ich weiß nicht, ob ihr schon davon gehört habt, aber nächste Woche findet die Nachhaltigkeitswoche statt. Das ist ein jährliches Event. Das wird von Studenten und Studentinnen verschiedener Hochschulen hier in Zürich organisiert. Und das Ziel ist, ganz verschiedene Aspekte von Nachhaltigkeit zu diskutieren, Workshops zu veranstalten und euch allen näher zu bringen. Und damit ihr so ein bisschen auf den Geschmack kommt, wollte ich euch kurz ein paar Events vorstellen, die stattfinden werden, aber das ist nur eine kleine Auswahl. Zum Beispiel haben wir am Montag einen Experten von der ETH eingeladen, um über Carbon Capture zu reden. Da möchten wir wissen, wie funktioniert das überhaupt, wie effektiv ist das, und da kann dann auch am Schluss diskutiert werden mit dem Professor. Dann für Leute, die gerne Geld investieren, haben wir auch etwas zu nachhaltigem Investieren. Da sind Finanzexperten, auch Leute aus der Wirtschaft, die da diskutieren und wo man quasi lernt, oder das Ziel ist zu eruieren, wie man sein Geld für die Umwelt anlegen kann. Und dann diese Woche ist ja wieder ein neuer Bericht des Weltklimarats erschienen. Wer wissen möchte, wie das funktioniert, dort dran zu arbeiten, wie das organisiert ist, für den ist das vielleicht interessant. Da haben wir einen der leitenden Autoren eingeladen, um darüber zu reden, wie die Arbeit am Weltklimarat ist und was auch seine persönlichen Erkenntnisse sind. Oder wer zum Beispiel wissen möchte, wie unsere Hochschulen hier in Zürich mit Nachhaltigkeit umgehen können, kann dieses Event besuchen. Das wird eine Diskussion mit den Rektoren der Zürcher Hochschulen, also die Uni Zürich, die ETH, die PH, die Zürcher Hochschule der Künste und der ZHW sein, wo die Universitäten darüber reden, was sie fürs Klima tun. Und zu guter Letzt, für alle Politikinteressierten, am Donnerstagabend wird es eine Podiumsdiskussion geben, an der wir zwei Wissenschaftler, also einen Klimawissenschaftler, den Herr Knutti, den vielleicht einige kennen, eingeladen haben, einen Politikwissenschaftler und 3 Politiker und Politikerinnen aus der Schweiz, wo wir darüber reden wollen, was die Schweiz für die Umwelt tut, was sie noch tun muss und wie das am effektivsten gemacht werden kann. Das war jetzt, wie gesagt, nur eine kleine Auswahl. Ihr findet das ganze Programm hier auf der Webseite. Da könnt ihr unter Veranstaltungen nach Wochentagen filtern. Wie gesagt, das waren jetzt größtenteils Diskussionen. Es gibt auch Workshops. Es gibt zum Beispiel auch Spaziergänge durch Zürich, wo man die nachhaltigen Orte in Zürich kennenlernt. Man lernt, wie man sein Fahrrad repariert zum Beispiel, um mit dem Fahrrad nachhaltig unterwegs zu sein. Ganz verschiedene Sachen. Da ist sicher für jeden was dabei. Danke für die Aufmerksamkeit.
Okay, so let's continue. For audience on Zoom, can you hear me? I didn't forget unmute myself, right? Okay, perfect. Okay, so let's continue, right? So we talk about relational calculus, right? How to write a logical formula to query my information organized as relational model, right? Now let's think a little bit deeper about the limitation, the caveat, and the power of doing that. So let's try to understand one question. That is, if I give you a relational calculus query look like this, is the answer always finite? Right? That's a fundamental question, right? I have a relational calculus query defined as what we are doing in the first half. Is the answer always finite? Very important, because otherwise you could have a query that never finish, right? And we are building something practical. We are not building a kind of mathematical logical like a formula on paper, right? We are doing something you need to get the answer from. Who thinks finite? Always finite. Who thinks so? It's almost like a trick question, right? So who think might not be finite? Okay. So now let's look at this. No, yeah. So think about the following query. This query. My query looks like this. My logical formula is very simple. That is, I want the product, PID, name, and price, but I want things that are not in that relation. Okay? It's a very simple query. This query will give you what? That depends on your database. But imagine you are evaluating this query on an empty database. Okay? It has nothing. The answer of this query is simply the domain to the number 3, right? Because you have no tuples in your interpretation. Whatever value I put into PID, name, and price, yeah, it's valid because they are not in product, because my product has no tuples, right? And remember, in the relational model, our definition is the domain is actually infinite. It has infinite amount of constant in the domain. This query will actually give you infinite amount of tuples in the output. So this is clearly something that we do not want, right? When we are building a practical system, we want to make sure whatever the user do, at least we want to check it, but hopefully the query language we gave to our user, whatever they do, gave them a finite amount of information. Hopefully, that means that they can finish, right? So we don't want this. And then we need to try to understand what should we do, because this type of query actually exists. So we need to constrain the power of our query language. The existence of such a query means that we are talking about a query language that's way too powerful. Okay? With a finite database, it is able to give you something with infinite answer. We need to constrain our power a little bit. And there are multiple ways that you could do. You could constrain the syntax, okay? And you could constrain the semantic. But before we talk about different ways you can constrain the power of this query language, let's try to define this more formally. We are going to define the notion of safe query and unsafe query. And then we are going to talk about how to constrain this with a semantic way, right? We are going to define a subset. Actually, not a subset. We are going to define an alternative semantic for relational calculus called domain-independent relational calculus. What is the safety of a query? So we say a query is safe if and only if for all finite database instance, evaluating this query on those instances will always give me a finite amount of tuples as answer. We can do some quick exercise. Is this query safe? A very simple formula, right? Not Rx, right? Well, and probably no, right? That's the same as the thing that we saw in the previous slides, right? This is not a safe query, right? If R has no tuple, this query is going to give me all the constant in the domain, which is infinite. How about this one? The logical formula is there exists Y and Rx or Ry. And then I'm interested, the free variable is X. It's the same, right? It's not safe at all. What about this query? My formula is there exists X, Rx, and my free variable is something I never saw before. It's not even there, right? As long as your R has at least one tuple, your answer is infinite. But whatever value you assign Y to, the thing in the formula is always true. There exists a tuple in R. And what about this one? You have Rx or not Rx, right? It's not safe, right? Because, yeah, whatever value you put X is always true. So these are a whole bunch of queries that's actually not safe. And as you can see, it's very easy for you to write a query that's not safe. It's not like you need to search for a whole bunch of queries and then you find some queries that are not safe. It's very easy for you to write something, right? That's why we really want to constrain our power to really try to understand whether we can define relational calculus in a different way, such that our user or yourself will not be worried about the safety of a query. So before we do that, how hard it is to decide whether a query is safe or not. Right? You give me a query, whether we can have an automatic algorithm to decide whether the query is safe or not. Because if I can do that, I can build a system tell the user, okay, the query is not safe. Right? Don't do that. I mean, that's one way to accommodate this. Unfortunately, it's super hard. It's undecidable. Okay? And we are not going through the proof, but if you are curious about how it's done, the reduction is from the first-order finite satisfiability. So from that problem, deciding whether a query is safe is actually undecidable. Okay? So it's very, very hard to do. So we need to do something else. There are two things we could do. Right? We could constrain our syntax to say, you cannot write that query. You can only write this smaller family of queries. We could do that, and we are going to do that later in the course. Another thing we can do is to redefine the semantics. So far, so far, we have a very natural semantic of relational calculus, right? I mean, we find all the assignment such that the formula evaluated to true. But that's not the only semantic. Given the same syntax, you can define different semantics. We can define a semantic such that every single evaluation of this query is safe. Let's try to do both. And we are going to look at semantics first. If you think about the fundamental reason that why query could be unsafe, I mean, my database instance is finite. That's not my problem, right? And that's finite. The fundamental problem is the answer of your query is a function of your domain. And because domain is infinite, that is the source of the problem. So one thing that we are trying to do is, can we define an alternative semantic for relational calculus such that it does not depend on the infinite domain? And that is something we call domain-independent relational calculus. It's very simple. So here's what we do. We define something called the active domain of a query and database instance. Okay, active domain is a function, take as input your database instance, which is finite, and also your query, which is finite because you can only type finite amount of word. Take these two finite things and give you all the constants in these two things. All the constants that appear in your database and all the constants appear in your query. And we call that the active domain. An alternative semantic of relational calculus is to constrain my answer to be only in the active domain. This is the alternative semantic. Okay? So essentially, when evaluate my query queue, right, I will always constrain that all the assignment that you can make on my free variable, that is all the result you could return to my user, must be taken from the constant that in this finite active domain. I don't want to see a constant that I never saw before in my database and in my query. So that is a very simple way for you to actually constrain this. So it's very easy to see that under this semantic, your relational calculus query is always going to give you a finite answer. Why? Because you have a finite active domain. Right? In the worst case, you get all the tuple in the finite active domain, but that's still finite. Right? This gives you a finite result, essentially under this semantic, right? So it's always safe. So now we see essentially three different query languages now. We see relational algebra, we see relational calculus, and we see domain-independent relational calculus. Now let's try to think about their relationships. So if put them side by side, right? So they are talking about the same thing, right? You have relational calculus on the one hand and relational algebra on the other hand. From the theory side, this is what we can show. The first statement is relational calculus is more powerful than relational algebra. And being powerful is not always good, as you can see, right? Because it includes things that you don't want to happen. Precisely what do we mean by a query language is more powerful than another query language? So the power of a query language is defined as the collection of functions is able to express. Okay? The more functions that a query language can express, the more powerful it is. So first statement that we could prove if we want, actually, we are going to prove that. It's very simple to prove. Is relational calculus as a query language is more powerful than relational algebra. How to prove that? It's very simple to prove. So you prove from two directions. The first direction is you first prove all queries you can write in relational algebra can be expressed in relational calculus. Hopefully that's something that's easy to show, right? How to show that, right? So we are not going to actually show it, but you do a recursion over the structure. Okay? For every single operator in relational algebra, you'll say, yeah, if you gave me that operator, that corresponds to this logical formula in relational calculus. Okay? It's going to be a very long proof, but it's very natural to see how to prove that. And then you prove the other way around. That is, we are able to construct some queries, some functions that you are able to specify in relational calculus, but you are not able to specify in relational algebra. Okay? And this direction is super, super easy to prove, right? Because in relational algebra, you always have finite answer, because, it's a finite amount of set operation over finite sets. Right? How can I get infinite answer? Every single expression in relational algebra is safe, but you are able to write a query that's not safe in relational calculus. So second thing is very easy to prove, right? You take all those unsafe queries that we saw in the previous slides. That's your counterexample, and that's not counterexample. That's your example for the second thing, right? So essentially, right, relational calculus as query language is more powerful than relational algebra. But that's not that interesting. What's actually more interesting and surprising is that if you look at domain-independent relational calculus and the relational algebra, a fascinating result that people showed almost half a century ago is they are equally powerful. Domain-independent relational calculus is as powerful as relational algebra. And that's something called Codd theorem. We are not going to prove it, but it just simply just beautiful, and people know that for half a century now. How to prove it, right? So you first prove all relational algebra expression can be expressed in domain-independent relational calculus by doing one recursion on the structure, okay? And then you go the other way around. You say all domain-independent relational calculus query can be expressed as relational algebra expressions, again, by doing one recursion on the structure of the query. So we are not going to show the proof because it's super long, and we are not going to put in the exam about how to prove it. But it's very important for you to know that every single query you are able to write in domain-independent relational calculus, you can find a corresponding implementation using relational algebra, and also the other way around. If you think about why this is super important, it's because it means that if you are building a system that user write relational calculus, your system can always find a concrete relational algebra expression to actually run it. It means that if you constrain the power of the user in domain-independent relational calculus, everything the user wants have a concrete correspondence of how to get it done. And that is the beautiful thing. you will never find a case that user give you a query that the system do not know how to answer. And that's the beauty behind this theorem. That is, domain-independent relational calculus is as powerful as relational algebra. That is why we are able to build a relational database system that the user write calculus, but system run it as algebra. So this is the fundamental theory behind a relational database system. And that is how we get the power here. Okay. Now let's talk about another caveat. It's here so far, I think I try to teach relational calculus by trying to convince you that every single query you are writing to the database is a logical formula, first-order logical formula, right? But I'm hiding a small thing when I talk about it. If you think about a relational calculus formula that we have been talking about, and a generic first-order logical formula, what are the difference, right? Is there any difference between these two things? And so far, I didn't emphasize the difference. I always focus on the similarities, right? But there actually exists a very, very fundamental difference between a relational calculus query and a first-order logic query. The fundamental difference, if you look at first-order logic formula, and if you go back to the definition of what is a first-order interpretation in mathematical logic, that thing could be infinite, right? You could have an infinite interpretation of your logic system. For example, you could have one predicate to say, this is all my integers. The interpretation of this under our world is infinite. It's countable, but infinite, right? But on the other hand, when we talk about databases, when we talk about a database instance, it's always finite, okay? So that's really fundamental difference between these two things. Why database instance need to be finite? Because I need to store it somewhere. I cannot put infinite number of things on my hard drive. It need to be there, right? So this is a fundamental difference. When we talk about the first-order logic, we always think about potentially infinite interpretation of your predicates. And when we think about our database system, we always think about a finite interpretation of your predicates. So that looks not like that huge difference, but there's a half century of theoretical study goes into this thing. So when you talk about database theory, the difference is we are talking about one field of study called finite model theory, because my model needs to be finite. And there are a lot of interesting things that are going to happen when you constrain your interpretation to be finite. Okay, we are not going into that. We can have the whole course about that, about finite model theory. It's kind of very different from what we see in first-order logic. We are not going to put this in the exam, right? So don't worry about this slides in the exam, but it's very important for you to know. In database, you are querying your fact using logic. But the logic system you are using inside a database potentially is actually very different from what you see last year in your mathematical logic course. Okay, now we have three query languages now, right? Relational algebra, right? Relational calculus, domain-independent relational calculus. We kind of know a little bit how to arrange them here, right? About which one is more powerful. Now let's try to talk about some alternative query languages, which are subsets of relational algebra and also domain-independent relational calculus. So this is what happens when we try to constrain the syntax to have something even simpler, okay? We are going to talk about a subset of relational algebra that only have selection, projection, join, and renaming. And we are going to talk about a subset of domain-independent relational calculus called conjunctive query. And magically, they are the same thing. Not the same thing, but they're equally powerful. Okay? So conjunctive query. Why do we want to constrain our relational calculus thing? I mean, that thing is good, right? So it's always safe. And whatever you can write there, I have a corresponding relational algebra expression. why do we need another query language? Well, one reason is there are a lot of problems about domain-independent relational calculus. It's still very, very hard to analyze. And they could be really important when you are building a system. For example, if I give you a query, and I want to ask, OK, does there exist a database instance such that it outputs non-empty answers? If you think about this question, right, it's actually not decidable for relational calculus query, even you take the domain independence semantic. And there are other questions. If I give you two queries, okay, phi1 and phi2, and I want to say, okay, are they equivalent? Are they the same query? Right? This is also turns out to be super hard. This is also undecidable for general domain-independent relational calculus query. Again, if you want to understand this question, which you don't, I mean, you don't have to as a system, but if you want to understand this, and if you want to get an efficient, practical solution for these two questions, relational calculus is too powerful for you. There are things in that family of queries that you don't know how to do these two things. And what's interesting is we are able to constrain your query language to make these two questions easier. Okay? And that's something that we are going to look at. One way to constrain your semantic is by defining something like conjunctive query, which look like this. It's a subclass of relational calculus query. The only difference is now I'm not allowing you to write arbitrary force-or logic queries. I only allow you to write a conjunction of predicates. Okay? This is the only query I allow you to write in your query language, in conjunctive query. That is, all your query phi is going to look like the following. It's going to be a conjunction between m different items. And I have a whole bunch of free variables, which you can only write a quantifier that exists. Right? And then that's your query. This is a subfamily of relational calculus because, yeah, I mean, why not, right? So, for example, if you have a relation like professor, professor ID and name, you have lecture, lecture ID, title, professor ID, right? How to get all pairs of professor and lecture, right, in which professor teaches the lecture, right? You can write a conjunctive query that look like this, right? It's pretty much conjunction. You have professor, you have lecture, right? These two tuples need to appear in both, and they need to match on the PID thing because they're the same variable, right? So this is one conjunctive query that you can write. So why do we need this? It's because once you constrain your syntax, you are able to have a lot of good properties, very interesting properties. So we are not going to put those properties in the exam, so don't worry about it. But I still want to take this lecture, let's look at those really beautiful properties that you can do in conjunctive query. So what are the things that become easier in conjunctive query? So conjunctive query, once you have that constraint, you can show that it is as expressive as a subset of relational algebra queries that only contains selection, projection, join, and renaming. Okay? So that's something you can show. Later, when you write the SQL queries, that is the same as a SQL query with select from where. That's the same class of things you can specify. Okay? So how to prove it? Well, it's actually not that hard to prove, right? So what do you want to do? You want to do two directions. You want to say, okay, any relational algebra expression with only these four operators can be expressed as conjunctive query, and also you want to prove the other way around. So the way to prove that is to establish this one-to-one correspondence in structure. Okay? You have your relational algebra on one hand, you have your conjunctive query on the other hand. So this is so if a relational algebra contains only single relation, yeah, that corresponds to that query, right? Which makes sense, right? So here is have R as a relation. There you give me all the X in R, right? And you can do more. You can have conjunctions, right? In the conjunctive query side, And each one of them going to correspond to these different operators in the relational algebra side. By building up this one-to-one mapping between these two query languages, you are able to prove whatever you can write in your query, you can write with 4 operators in relational algebra, and whatever you can write on the left-hand side, you can also write it on the right-hand side. So, and there are also other properties that are interesting about conjunctive query. Also interesting about all the select from where query you are going to write in the next lecture in SQL in practice. Conjunctive query is monotonic. Okay? That's another property that's interesting. What do I mean by that? Essentially, if you give me 2 databases, I1 and I2, if I1 is a subset of I2, meaning that in the second database, I only have more tuples, okay? I have a superset in my second database. I know more. I know strictly more in the second database. And given any conjunctive query Q, you can also show the result of this query on the small data set is always going to be a subset of the result of this query on the big data set. Whatever query you write, you have this monotonic property coming out of this query language. How to prove it? Well, it's kind of easy to prove, right? Assume you have a conjunct query look like this, right? So what we are going to show is, okay, what do I mean by some tuple is in the result? Yeah, it means that you are able to find all those variables in the quantifier that make that formula true, right? And once that's true, you use some property about kind of the containment of these 2 databases, right? You go back, you read it. It's very easy to prove. It's not that hard, right? So, and also not that surprising, right? Because pretty much all the operations you have in relational algebra, in the conjunct query type of thing, they are kind of monotonic in a way, right? So when you know strictly more facts, you have strictly more answer, right? So this is pretty much on the theory side, right? So we have these 5 query languages. Now, this is not a theory course, right? This is the goal of the course is not to do theory, but to make sure you can use the database in real world. But given this theoretical foundation, we are going to talk about some practical query languages. Not only you can write on a piece of paper as a formula, but also you can write that in a real system. And that is something called SQL. Okay? The way we are going to talk about SQL, we have a different structure with the book, is we are going to talk about 3 different subsets of SQL. There's a subset that's going to give the same power as conjunctive query, give you the same power as relational algebra with only that 4 operators. And then there is a subset of SQL query that give you the same power as relational algebra or domain-independent relational calculus. And then there are things go beyond it. Okay? That's why we talk about auto theory, because I really want you to know every single SQL query you are writing under the cover corresponding to some theoretical class of query languages. And then we can actually reason about the property. Okay? So now let's talk about SQL. Right? There's going to be a pretty dramatic shift of how we think about query language. So far, we think about them as, there's some relation somewhere, it's a mathematical object, and the query is a mathematical formula, right? Now we start to think about them as something you can interact with on a real computer as a real user. And that is like SQL. So now we are going to learn a new programming language, essentially. Very high-level one, but still a programming language. So I think from your experience so far, right, whenever you are learning a query language, learning from lectures is the worst possible way to do that. Right? There's no way I can teach you how to write C++ by just telling you what to do, right? So the only way to learn that is to practice. And if there's something that you're not sure about this, read the reference, read your book, or Google it, okay? So I hate to say this, but this is probably the only way you can actually learn a language. In this course, we are going to have some hands-on session to make sure we write SQL query together. You have the practice, but there's nothing I can do to replace the process of you kind of open a database and practice, okay? So next week, we are going to write SQL query together. Hopefully, that's part of the practice, but it's not going to be enough, Okay, like you need to write SQL query by yourself, right? You need to read deep, like read the whole chapter 6 of the Stanford book. That's not something that I can cover in the lecture because there's so many corner cases, there's so many things that it's very hard to describe, right? So there's no way to go around that. You need to do that. The goal of the lecture, why are we here, is to give you the framework of how to think about those queries, to make sure whenever you are reading the book, it becomes clear why they are talking about what they are talking about. Okay, and what is the connection between all those query languages and all the theory, how to connect them. That's the goal of the lecture. Okay, but to really learn this language, you need to practice. Okay, now let's talk about SQL. First one is the wrong pronunciation of SQL. It's supposed to call SQL, but anyway, yeah. So before we talk about what SQL looks like today, let's think about if you live in 1970s. You are building a practical system to make sure the user can store their information in relational model and also can query it using relational calculus. What type of system are you going to build? If we start from scratch and try to enable this functionality, you are probably going to have a query language look like this with 3 different components, right? I have a database, I have a relational database, right? And then I have a query language, give me an answer. There are 3 things you need to define. You need to tell the system how to define the schema, right? This is what my data looks like. You need to tell the system how to put information into the table, right? Because you need to give the user some way to do it. You need to define a query language to make sure user can actually write that. If you were to build a language in 1970, this is probably what you are going to have. And so magically, that's what SQL also have. There is something called data definition language, which is a subset of SQL that try to define the schema, try to specify a relational schema to the system. There is something called data manipulation language to try to manipulate the data, to try to insert tuples into your relation or update tuples in your relation. And then there's the query language to write relational calculus expressions in a human understandable way. So these are 3 components of SQL, and we are going to go through them one by one. So just some quick history of SQL, right? The whole thing started in 1974. The reason we read like SQL is in the original paper is really called SQL, right? SQL. And then, so that's a very old paper. And then there's the SQL standard back in 92, with a whole bunch of standards follow up. People start to kind of enrich the language, right? In 2006, you have XML, right? In 2008, you have a whole bunch of things. In 2011, there's a whole bunch of SQL standard, right? Over the history. So today, there's a whole bunch of databases implement part of the SQL standard, okay? So that's a relationship between the system and the SQL standard. They actually implement, all of them implement a slightly different subset of standard with a slightly different syntax, right? So the different database engine might have attention that's unique, right? So in this course, we will use PostgreSQL as the reference, okay? So, but in practice, when you are really using a database system, for example, if I use MySQL, right? So try to make sure, don't be surprised if the query needs some special consideration given like compared with what we have in this course. But they are all very similar, and they implement the same standard, but yeah, they are also a little bit different here and there. Another thing that's important before we start to go to the system side is, so far when we talk about relational calculus and relational algebra, we obviously think they have a set semantic, because that's simpler, easier to describe on the theory side. We don't need to re-educate everyone, including myself, about how to do bag operations. I don't know how to do bag operations, to be honest, right? So it's very hard. It's a lot of detail that we don't want. We don't need to go into details. So, but each relation in SQL is a bag of tuples, okay? So that is a fundamental difference to keep in mind. Okay, Now let's talk about the fourth subset of SQL statement you can write. And that is for you to define the data schema. It's called data definition language. So what can you do here, right? So this definition language provides statements to define a relational schema. So recall that in theory, right, when we want to write this on a piece of paper, this is how we write a relational schema. It has a name, has a whole bunch of attributes. For each attribute, have a domain, the data type, right? In SQL, you need to provide the same thing to the system: the name, the set of columns, and their type. So like all the language, like almost pretty much all the query like programming language, you have different data type. You have character, right? You have integer, right? You have blob for large binary like piece of data, so on and so forth. You have date, for example, right? Whole bunch of data type. So when you define this schema, is look by have something like this. So you create a table, which actually is something you write in the system, which is amazing because it's human understandable. You create a table with the name, professor, contains 3 different attributes: personnel number, which is integer, that's a data type; the name, right, which is string; and the level, which is 2 character with some default value. And then you have a primary key, which is a personnel number. When you write this in your database, what you are going to define is a relation that actually look like this. This is what we wrote last week, right? You can write that down on a piece of paper. The thing on on top is what you actually write to a real-world database system. So you can see the correspondence, right? So whatever we need to define in a relational schema, the create table statement can get it done. Okay? You can also delete a relation. You create a table, you can also delete a table, right? So if you have a professor table you want to delete it, you just drop table with a table name. Okay? You can modify the structure of the relation. For example, you say, yeah, I want to have 1 additional attribute to my relation, right? How can you do that? Well, I mean, you can add a column, right? So the thing you are going to do is you can alter table, right, with a name. You can say, I want to add column, you put a new column, right? So I can see it's very easy to understand. I mean, that's actually the beauty of SQL, because that's something that, yeah, like it's human understandable, right? But what's also more beautiful is every single thing you are writing there that's human readable, corresponding to a very precise logical representation as what we've been talking about in the last 2 lectures, right? That is the beauty. So another thing that is, assuming you have database, you add a column. What are the information, like what value the database is going to fill, like for the new column, right? So essentially, if you have a default value in your SQL query, when you alter the table, the database is going to put in the default value, right? Otherwise, it will keep it as empty. So in the next lecture, we are going to define formally what do we mean by keep something empty, okay? But right now, just think in the most natural way that that thing is empty. That it means I don't know what the value is, okay? And you can delete a column. You can delete the attribute. You can alter table, professor, drop column age, for example, right? You can drop a column, yeah. There are more, okay? The best way to do it is if you want to add a column to your table, you just Google SQL add column, it's going to give you something like that, okay? This is the best way I know about how to write it. Whenever I write alter table, I just Google that. So also go back, read the book. There's no way we can go through all the syntax of this, right? But hopefully this tell you essentially underneath the cover, when you write that query, what you are doing is to define the relational schema that we have been talking about in the last lecture and also what we have talking about today. So let's look at one example, right? So assuming you want to create a database that looks like this, what should you do, right? Yeah, you create a table, professor, with these 4 attributes. Each one of them has a type. You define the primary key, right? And then you have this student table. You have this lecture, requires, attends, and tests, right? So this is how you define, essentially, the schema of a database on the left-hand side. It's very natural, right? So second subfamily of queries you can write, the goal is really try to put information into the table that you just created, right? Because whenever you are creating a schema, that table is empty, there's nothing there, right? You need to put something there, right? Otherwise, what are you going to query? So this goes to the second subfamily of SQL, that is data manipulation language. So if you want to insert information into your database, right, there is a statement called insert into, right? The way you are doing that, you insert into a table name, you specify the attributes you have value for, right? And then you put the values in the end, right? If you run, for example, this SQL query over this database instance, right, it's going to give you essentially one additional student in this table. So one thing that's interesting is in this table, it has 3 different attributes. But in the SQL query, we are only specify the value for 2 attributes. What should the database put in the 3rd attribute, semester? Well, that depends. If you define the default value when you are defining the schema, the database is going to put the default value. If you do not specify default value in the schema, the database is going to keep that empty. Okay? We are going to define what empty means. Next lecture is going to be actually very, very beautiful. And that's a way for you to tell the system how to say, I don't know. Okay? That's a very fundamental problem, but that's Friday. Okay? So far, empty. You can also delete tuples from your relation. For example, say, yeah, I want to delete all the students with a semester larger than 13, for example, right? So essentially, you have delete, that's the keyword, followed by the table name, and you specify some conditions that you want to be true, right? And then you can also update your relation. So here, if you say update student, set semester equals semester plus 1, right? What you are going to do is take all the tuples in this relation, take them, increase their semester value and put them back, right? So that's the way to think about it. So, and in general, right, so what data manipulation language allows you to do is to allow you to do the process usually called ETL. You extract data, you transfer data, and you load it into the database. So that's the 3 important steps. Okay? So populating a real-world database is kind of interesting because if you think about the data we are dealing with today, they are often like terabytes. There's billions or millions of tuples. Right? Doing them tuple by tuple is often very slow. So that is why in most of the database system, you are able to do that in a bulk way, right? So in a different way that you put all those data into kind of a couple terabyte of file and load them at once. Okay? So most systems actually give you this functionality. They also give you functionality to actually get data from some file, transform them, and also just load them together into a database table. So that's all for today, right? On Friday, we are going to continue to talk about SQL queries.